This lesson will examine the basic laws and principles of physics which govern aerodynamics. One of these fundamental laws is that energy and mass can be neither created nor destroyed, but only changed from one form to another. This is the basis of the principle of continuity, and to demonstrate its effect on aerodynamic theory, we will consider a stream of air flowing through a tube which has a reduced cross-sectional area in the middle. The air's mass flow, or mass per unit time, will be the product of the cross-sectional area of the tube, A, the velocity, v, and the air density, ρ. The mass flow will remain constant at all points along the tube. The equation of continuity is A times v times ρ equals constant. Because air is a compressible fluid, any pressure change in the flow will affect the air density. However, at low subsonic speeds, less than Mach 0.4, density changes are insignificant and can be disregarded. The equation of continuity can now be simplified to A times v equals constant, or, when we rearrange it, velocity equals constant divided by area. Because the mass flow must remain constant, it can be seen from the equation of continuity that the reduction in the tube's cross-sectional area results in an increase in velocity, and vice versa. The equation of continuity enables the velocity changes of airflow around a given shape to be predicted mathematically for speeds below Mach 0.4, which is around 260 knots at sea level. Associated with the principle of continuity is Bernoulli's theorem, propounded by 18th century Dutch-Swiss mathematician Daniel Bernoulli. His theorem states that, in the steady flow of an ideal fluid, the sum of the pressure and kinetic energy per unit volume remains constant, or, more concisely, the sum of the energies present remains constant. In this context, an ideal fluid is both incompressible and has no viscosity. The theorem can be expressed as pressure plus kinetic energy equals constant, or P plus half rho v squared equals K. Let us consider a mass of air at ISA conditions, moving at 100 knots or 52 meters per second. Static pressure is 101,325 newtons per square meter. Density 1.225, giving a dynamic pressure of 1656 newtons per square meter. Pressure energy 101,325 plus kinetic energy 1656 equals a constant 102981 newtons per square meter. Because the velocity of the airflow at the throat has doubled, its dynamic pressure has risen by a factor of 4, and the static pressure has decreased. But the total pressure, the sum of static and dynamic, has remained constant. This constant can be referred to as total pressure, stagnation pressure, or pitot pressure, according to context. The tubes used in the diagrams just shown are used only to demonstrate the principle of continuity and Bernoulli's theorem, and are not devices which could make an aeroplane fly. However, an aerodynamic force to oppose and exceed the weight of an aircraft can be generated by a specially shaped body called an aerofoil. The airflow over the top surface of a lifting aerofoil will be at a greater velocity than that beneath, so that the pressure differential will result in a net upwards force per unit area. The bigger the surface area, the larger the force generated. Next, we shall see the similarity between the flow over the aerofoil and the flow through the tube used in describing the principle of continuity and Bernoulli's theorem, and that these fundamentals still apply to aerofoils. A streamline is the path followed by a particle of air in a steady airflow, and one streamline cannot cross another. When they are shown close together, it indicates increased velocity, and when wide apart, decreased velocity. When streamlines diverge, it indicates decelerating airflow and the associated rise in pressure. And converging lines, acceleration with decreasing pressure. A stream tube is an imaginary tube made up of streamlines. There is no flow into or out of the stream tube through the imaginary walls, only a flow along the tube. This concept will help you to visualize the airflow around an aerofoil. To grasp the basic principles of aerodynamics, you will need to understand the principle of continuity and Bernoulli's theorem. We can summarize the relevant elements as follows. By the principle of continuity, air accelerates when the cross-sectional area of a streamline flow is reduced, and decelerates when it increases. By Bernoulli's theorem, if a streamline flow of air accelerates, its kinetic energy will increase and its static pressure will decrease. Conversely, if air decelerates, the kinetic energy will decrease and the static pressure will increase. Additionally, it should be remembered that these pressure changes will not affect air density at speeds below Mach 0.4. By using these effects, an aerofoil can generate the aerodynamic forces required for flight.